Hey everyone, in Physics 40S, it is Dr. Carroll here. We got Unit 8, Lecture 3. We're going to look at electromagnetic induction and transformers. That'll lead into alternating current. Alternating current will be coming up, not in this lecture, but coming up. So, we know that if you have a wire that carries current, a magnetic field will be created. Well, what if we move a magnet through a coil of wires? Guess what? You will get a current created, an induced current. And this was exciting stuff for guys like Oersted and Lorentz and all these other guys. And it was Henry was another guy, last name Henry, who realized this was a really exciting thing and would lead to alternating current. And Nikola Tesla was certainly part of that movement, and there was all those current wars between him and Thomas Edison, and some interesting stuff for sure. See some movies about that. So let's read along here in our book, and now I'm looking at the booklet, and this is page 55. Okay, so how do we get an induced voltage and induced current? Although a steady magnetic field produces no current in a coil of wire, so if I just put a coil of wire near a, let's say a bar magnet, right? It's a bar magnet, you got a north pole and a south pole, and you have no motion between them, you just have a coil of wire here, then there will be no current generated. But if you move the coil, cut it through the bar magnet, so a changing magnetic field can produce an electric current. And this current is called an induced current, I induced. And an induced voltage is also created. So as you might expect, the induced voltage, well, here we used an E. I'd rather use this course of V. So V induced equals I induced times R. V equals IR. It's Ohm's law. The whole process is known as electromagnetic induction. Now, magnetic flux, I don't think we have to recall that, unless you heard about it somewhere else, but for the first time, magnetic flux talks about the interaction between the magnetic field and an area of wire. And it turns out to be BA cos theta, which is actually the vector dot product of B and A. We talked about with the F is BIL sine theta about vector cross products. Well, this is a vector dot product. And you will, if you're taking more physics, end up taking a vector analysis course, I would think, I would hope, and you will learn about the differences between dot products, where you see cosines, and cross products, where you'll see sines. Anyways, theta is the angle between your magnetic field vector and the area vector. So that's a new concept. What do you mean by an area vector? When you think of an area, you think of a scalar, right? A football field has so much area. 100 meters by, I don't know, 75 meters get multiplied together, you get the area of the football field. What are we talking about here with the direction? Well, it is helpful in physics, in terms of reference, to create an area vector, which is simply a vector drawn normal, also known as perpendicular to the surface of a coil. So in this example here, I have a coil, circle here, a bunch of wires all tidied up, and then your A vector, your area vector, is just drawn perpendicular to that surface. So if you're that was a circular coil, I could have a square coil, fine. If my magnetic field lines and my area vector are pointed in the same direction, then I will get the maximum penetration of the coil through the magnet through the coil is relative motion, so your phi, your magnetic flux, is just B times A. That's the maximum interaction because the cosine of 0 degrees is 1. Okay? If rather I slide the coil so that the magnetic field is perpendicular to the area vector, in other words, the magnet moves parallel to the coil, right? So the magnet is moving parallel to the coil, then I get theta of 90 degrees, and there is no flux. Okay, no flux linkages because cosine of 90 is 0. In general, phi is BA cos theta. So Michael Faraday came up with this law of induction, which says that the induced voltage, V induced, and that's the symbol I'll use, turns out to be minus N, where N is the number of coil turns. The minus sign has to do with Lenz's law. We'll get to that later, perhaps, if we have time, times the change in flux over the change in time. You can see how eventually this all relates to calculus because we're talking about time rates of change, which is derivatives. So, or minus N, phi final minus phi initial over T final minus T initial, but phi is BA cos theta. So minus N delta BA cos theta. N is the number of coil turns, phi is the flux, the units are Weber, named after another scientist. That's a capital W and a little b. Capital W, little b. And there's Ohm's law, I induced is E induced times R. Now in many examples, the area of the coil stays constant, and we're talking about maximum induction, so theta is 0 degrees. So then my area stays constant, so it can be brought in front of the change sign, and my cos theta becomes 1. So I get the induced voltage, E induced, which is let's call it V induced, is minus NA delta B by delta T. So the greater the change in magnetic field strength per time, the greater the induced voltage, the greater the area of the coil, the greater the induced voltage, the greater the number of turns of the coil, the greater the induced voltage. So how do we apply all this? I mean, it's all leading up to generators. A 150 turn copper coil is moved relative, AC generators. A 150 turn copper coil is moved relative to a bar magnet, theta 0, and a change of flux linkage of 3 by 10 to minus 5 Webers occurs in 100th of a second. Calculate the well, we keep saying E induced, that's the same as V induced. So it's minus N delta phi by delta T. So 150 turns, change in flux, 3 by 10 to minus 5 over 0.01. And you get 0.45 volts. The negative sign, we can worry about that later. I won't mark you wrong if you leave it out. Just the induced voltage is 0.45 volts in this example. Now, the magnetic field could be changed simply by turning a switch, right? It could be 0, then you turn on a switch. If it's an electromagnet, the magnetic field increases to some value, and you induce a voltage and a current. And the current is in part B here. If the coil is offering 100 ohms of resistance, so I induced is E induced over R, so 4.5 by 10 to minus 3, just 0.45 over 100. So you induce a current in that coil of wire. Okay, so that's the first example. Now let's look at a second one here. We have 325 turns. The change in flux is 11.5 milliweber, 11.5 by 10 to minus 3 Weber, and delta T is 1 millisecond. So E induced, which is the same as V induced, I won't keep saying that, minus 325 times 11.5 by 10 to minus 3 over 1 by 10 to minus 3, minus 37.5 volts. That is a big value, isn't it? Let's look at a third example. Here we are on the top of page 57. We have an induced voltage of negative 0.25 volts. We know the change in flux is 5 by 10 to minus 3 Weber. We know delta T is 1 second. Those are all given. You solve for N. So doing the isolation, N is minus E induced, so minus 0.25. Let's write it like this. Minus V induced delta T over delta phi, capital Phi, or E induced, let's call it V induced, and you get 50 turns. Okay, so you can get the number of turns of the coil. Fourth example, we have just 2 loops, so N equals 2, and they tell me the flux changes from minus 20 to 25 in 0.25 seconds. So my change is 25 minus a minus 20, so 45 Weber in a quarter of a second, and minus 2. So minus 2 times 45 over 0.25. Minus 360 volts is my induced voltage. Okay. Fifth example, here we have a square coil. That's interesting. 75 turn square of coil, length is 4 centimeters. You start in a magnetic field bath of 1.5 Tesla, and then you shut off the magnetic field completely. So it goes to 0 in 0.025 seconds. Okay, that's my delta T. Theta is 0, so cos theta is 1. So the induced voltage is minus NA delta B by delta T. Right, that's my V induced equals E induced minus NA delta B by delta T. So I know N is 75. I know delta B is minus 1.5. I know delta T. Now how do I get the area? Well, all I do is it's 4 centimeters or 0.04 meters on a side. So I just square that. So 0.04 squared, just going to use my calculator. Here we go. 0.04 squared is 0.0016. So this was interesting. If I wanted a circular coil, I will do area is pi r squared. But for a square coil of wires, I will do just square the length of a side. So my induced voltage is 7.2 volts. And here we have example 6. We have 20 centimeter diameter, so the radius is 10 centimeters, or 0.1 10 centimeters. What's 10 centimeters? 0.1 whole meters. 10 divided by 100 is 0.1. Okay. Circular loop of wire is in a 0.06 Tesla B field, then it's removed in 0.1 seconds. Okay. The faster you remove it, the greater will be my induced voltage. Calculate the induced voltage. So it's a loop of one wire. So N equals 1 pi r squared. Now what do I have? 1 by 10? Oh, that's 10. That's 10 by 10 to minus 2 squared times pi, right? Area is pi r squared. Area is not, A isn't for amperes, it's for area. I know that's going to be annoying, but that's what it is. So area is pi r squared. So I'm going to take pi r squared. So 20 centimeters, the radius is 10 centimeters. 10 divided by 100 is 0.1 squared times pi times 0.06 divided by 0.1. Oh, it's all negative, right? Floating decimal is fine. 0.019 volts. Okay? So that is the story on that one. Okay, so those are using Faraday's constant. No, sorry, Faraday's constant is something in electrochemistry. Faraday's law of electromagnetic induction. Now, we're going to look here on page 58 on transformers. Now it says see the whiteboard. Well, I'm going to make the whiteboard right here. So a transformer uses mutual induction. Okay, so what you have is typically an iron ring. So I'm going to draw that out here. Iron ring. It's also called a yoke. Y-O-K-E. Okay, and in the iron you have one coil of wire and a second coil of wire. And you input, oh, maybe you're plugging it into a regular AC outlet in North America and it's 120 volts, but then you want the transformer to power something that is a lot less than that, let's say 10 volts. So the 120 volts, that's your input or your primary, and coming out your 10 volts, that's your secondary. Now this will annoy the heck out of you, but guess what letter we use for primary? Capital P. For secondary, capital S. And you want the number of coils to be different. There's two kinds of transformers, a step up where the voltage increases, so the voltage goes up, and the one I've drawn here is a step down transformer, so the voltage goes down. So typically when you're generating electricity at a power plant in Northern Manitoba, let's say, you'll start with a step-up transformer, so the electricity will more easily be transmitted from the generating station to the substations in the city or the town where you're delivering the electricity to, and then in the substation you'll be stepping down to get to a house transformer, which will be 240 volts, and then some of your appliances of course run on 240 volts like your stove, but others run on 120 or even less, as we're talking about here in this example. So you have step up and step down transformers. Now the transformer equation is this: the voltage in the primary over the voltage in the secondary equals the current in the secondary over the current in the primary equals the number of turns in the primary over the number of turns in the secondary. That's known as the transformer equation, and if you really want to be a stickler about this, you should write root mean square, RMS. You'll sometimes see that written because we're talking about alternating current really here, and that alternating current creates the linkages between the primary and the secondary coils, creates our transformer induction effect, if you will. Now if you cross multiply it, you see that VPIP, let's just look at the first part, VPIP equals VSIS, and power we know is I times V. We know that from our last chapter. So we're saying that in a 100% efficient transformer, you are not losing any power, you are just transforming it. That's where the word comes from. Not about Optimus Prime or the Decepticons. We aren't going there. Okay, so VPIP equals VSIS. So let's say, let's keep going with this here. Let's say the incoming current was 5 amps, and let's get the secondary current. So your IS would be VPIP over VS in this example. So VP is 120 times IP is 5 over VS is 10. So that's 12 times 5. So it's 60 volts. Now I said I wanted it to be 10 volts. So let me just cheat and say suppose we wanted it to go down to 60 volts and not 10. Okay, so you see here that the turn ratio, the NP over NS is turn ratio, would be VP over VS would be 2 to 1. So there'd be twice as many coils in the primary than the secondary. So the turn ratio, now some people write the turn ratio as NS over NP, so be careful what you have here. So NP over NS, let's just call it that. If I want the turn ratio primary to secondary, would be 2 to 1, because it would be 120 over 60. Okay, let's do another one. I'm going to go to a fresh page in different program. This is the first time I've tried this. Let's see if it's going to work. I'm a little nervous about it. Oh, I didn't want that. There you go. Okay, good. Okay, there we go. So let's do another example with transformers using this paint program. So let's say my incoming voltage was 120 volts and my primary current is 7 amps. That's not area vector, that's 7 amps. And by the number of turns in the primary is 3. There's no units, just 3. And the number of turns in the secondary is 12. Let's calculate VS and IS.
I found this on the web.
Okay.
There's 33
well,
and the number to the secondary is 12. Let's calculate versus
well,
check it out.
what? Okay. Once in a blue moon, Siri just starts to talk to me, and I don't even have a phone. I'm not quite sure what that's all about. Anyways, so I want to solve for VS. So VS, well, I have the turns, so I'm going to use that one. Right here, let's write it again. VP over VS equals IS over IP equals NP over NS. So my turn ratio, 12 over 3 equals 4. So that's good. So I know that VP over VS equals 4. So VS equals VP over 4, which is 120 over 4, which is 30 volts. So this is a step down transformer. Okay, this example is a step-down transformer because the voltage has gone down. And I can get IS here. IS over IP equals 4 as well. So IS is 4 times IP. So 4 times 7 is 28 amps. So the current goes up and the voltage goes down, but the products of them have to be the same, right? VP times IP. Sorry, not the what am I saying? VP times, yeah, 120 times 7. And what's VS? 30 times 28. 30 times 28. 30 times 28 is 840. 120 times 7 is 840. Now, as you can imagine, it works fine. Transformers, in an ideal case, are 100% efficient, but in real life they aren't. And they get hot. And you can just touch, if you have an old school modem, right? Or scanner, those big plugs, big box plugs, they get hot because there is internal resistance, there is other effects which cause a heating and a loss of energy. You can try to mitigate that loss by, what's the word I want here? Laminating, that's right. You laminate the iron core, and that creates these little currents, little eddy currents, which fight against each other. So there's gimmicks, there's ways to minimize the heat loss, but there's always going to be some heat loss. Also, some of the older industrial transformers used to use this polychlorinated biphenyl chemical as a coolant, and that is a really nasty chemical and caused all sorts of problems. So we'll have a worksheet soon which will have some transformer problems on it. It really is a useful, interesting bit of information, and if you've ever gone traveling to Europe, you know that you may, depending on your electronics, especially curling irons and hair straighteners, need a travel transformer. So it will make an appliance that was working on 120 volts operate on 240. Now, lots of laptops nowadays have dual voltage, so you don't need something like that. Be careful, there's something also called a plug adapter, which just makes the end of the plug fit in to the outlet in the country that you're at, but it doesn't change the voltage. So just changing the shape of the plug is not going to change the voltage. And I'm sure there's been many people who have fried their electronics because they have not paid attention to the idea of transformers and adapters. Adapter may, in addition to changing the voltage, change from AC to DC or from DC to AC. Okay, so let's try another one. I'll go to File, New. Actually, a new concept here. Let's get this a bit larger. Okay. Another discussion about induction. If I have some metal rails here, and I have a metal rod, like a rolling pin, and it's of length L. And let's say I have a magnetic field in this region here, B. If I now push that rod, I will get a velocity. So it's going to be moving through the magnetic field, just like an airplane wing moves through the magnetic field of the Earth. And guess what you form? Now this is very E-motional, E for voltage, right? E-motional or V-motional voltage, capital V for voltage. This is little v for velocity. So that becomes B times L times V. And you can look up the proof if you want for that. So you actually get a voltage across the ends of the rolling pin that is proportional to how fast the metal object is going times the length of the metal object times the strength of the magnetic field. The stronger the magnetic field, the greater the length, the greater the voltage. I should say, as I was thinking about all this, about metal detectors, you sometimes see guys at the beach who spend 7 hours with a metal detector to find like 25 cents from, but it was from 1941, you know, they get excited about it. maybe you're one of those people. More power to you. So this kind of equation is interesting, and let me do one example here, and it'll be on a worksheet that I'll give out soon enough. So let's say, here's my example. Let's say I have a length of 3 meters and a magnetic field strength of 0.07 Tesla. Then, and my speed is 7.8 meters per second. So I want to get E motional or V motional. So it's BLV, so 0.07. You can check the units on yourself. See how it gets out. 0.07 times 3 times 7.8. 0.07 times 3 times 7.8. And you end up with 1.638 or 1.64 volts. Okay? So we threw in some equations here as we looked at the preliminaries of electromagnetic induction, Faraday's laws of electromagnetic induction, how it relates to transformers, how it relates to this rod rolling on the rails, and that's a good place to stop for now. Okay, have a good day, everyone.